Did you want to introduce the first speaker?
Yeah. All right. So welcome back. I hope you all had a good break, a nice coffee for some of you. So we start this session with Gonzalo Torroba. He's going to tell us about hyperbolic compactification of M theory and de Sitter quantum gravity. Please take it away.
Okay, thank you very much. I'd like to thank the organizers for putting together this wonderful conference. It's really helpful in these difficult times. And also thanks for the invitation to speak. I also want to acknowledge my collaborators in this work, Bruno, De Luca, and Eva Silverstein. And yeah, let me turn off, as I said, my camera so I get a better connection, but I'll turn it on in a little bit. So, one of the central problems in theoretical cosmology, as we know, is to understand the accelerated expansion of the universe. And especially, we would like to be able to have a framework to understand quantum gravity in such cosmological spacetimes. Our approach to this problem proceeds in two steps. So first, try to find de Sitter solutions in string or M theory, and then understand them as the formations of ADSCFT. So if one succeeds in uplifting ADSCFT from negative to positive cosmological constant, then that would provide us with a holographic formulation of cosmology. So that's a broad plan. Now, in this talk, it will be a bit more specific. I'll present a simple mechanism we have found very recently that yields de Sitter solutions in M theory, and it uses a very, very minimal list of ingredients, especially hyperbolic manifolds and Casimir energy. So it's based on this paper here. I do want to apologize because I only have time to cover this paper. And of course, this is a very exciting area with many interesting and new results. So hopefully we'll have more on that in the discussion sessions later today. Let me begin with a brief overview of the framework. So in string or M theory, we look for solutions of the form, some d-dimensional space-time that we want and some internal space. We have to solve the Einstein plus matter equations of motion to find this. But it's usually very helpful to think about a slightly simpler problem, which is a homogeneous dimensionally reduced potential, where we are just integrating the different energy sources over the internal space. And then we get to understand how these sources compete or how they can be used to find useful solutions. Okay, and let me super briefly review how the standard ADSCFT energetics works when we do this. So remember, generically we have some color branes, and as we know, these space-time directions combine with the radial direction to give ADS, and the internal manifold that had positive curvature gets stabilized at a constant size. Now it's nice to understand how this arises from this homogeneous potential. What happens there is that there are two energy sources that are contributing. The positive curvature of the internal space contributes negatively to the potential, so it's trying to shrink, say, the sphere, while, of course, the flux lines are getting squeezed if we try to shrink the sphere, and they contribute positively to the potential here. Okay, note that I'm plotting the potential as a function of 1 over the internal size. Okay, and out of the combination of the two, we get a minimum with negative cosmological constant that corresponds to this ADS solution we're looking at. So the idea to uplift ADS-CFT to cosmology in perturbative string or M theory is then to change this first contribution that had positive curvature into a manifold that had negative curvature, because that would contribute positively to the potential. Okay, and then we have to find an appropriate source of negative energy that sits in between this curvature contribution and the flux contribution. Okay, and by working enough, one can try to put together these three types of ingredients to find solutions with positive cosmological constant. Let me remind you of the well-known Dine-Seiber mechanism that says that we know in string theory the potential will go to 0 into the compactification limit, and that's why you see that the potential is 0 here as a function of 1 over r. Okay, so that means that if we find a de Sitter minimum, it will be metastable. Okay. So many years ago, we gave a proof of principle that this works in type 2b. We found the S3 solutions. Okay, these solutions, this solution was consistent, but used a somewhat complicated list of ingredients. Today, the goal will be to present a DS4 solution, so in the realistic dimension we care about, with a simple list of ingredients as it can get. So what is the setup and the stabilization mechanism? So we work in 11-dimensional supergravity limit of M theory. This source of uplift of the positive first contribution to the potential will come because we'll compactify on a finite volume hyperbolic manifold. Okay, and then we'll argue that the appropriate source of negative energy actually comes from Casimir energy that is localized in small cycles where we put antiperiodic boundary conditions for fermions. And we'll get the n units of a certain flux, which means we have M2 branes around. For the side of the hyperbolic geometry, let me just remind you that if we are thinking, for example, in terms of H7 in the upper half plane metric, then we can get a finite volume hyperbolic manifold by modding by a freely acting subgroup of the isometry group of the hyperbolic space. Okay, and for our purpose, these manifolds have a very important property called Mostow rigidity, which says that the hyperbolic structure is uniquely fixed in terms of topology. Okay? For us in particular, it implies that all metric fluctuations, except for the conformal mode, are gapped. And that's a really huge simplification if we compare to other compactifications that start their life with many moduli that one has to worry about. So here we'll basically have to worry about the conformal mode. Okay, so let me now briefly describe the source of negative energy. As I said, it will come from Casimir energy. So the idea is that these hyperbolic manifolds have small cycles. In those small cycles, we'll put antiperiodic boundary conditions for fermions, which means that the Casimir energy is dominated by bosons, and so it's net negative. Okay. One way to get these small cycles is from near cusp regions in the hyperbolic geometry. And here I'll locally describe such a region. So it has some radial direction, and then it has some toroidal cross-section that is decreasing with this exponential factor that accounts for the negative curvature of the space. Okay. So the idea is that we have some compact manifold. There are various of these near cusp regions that are glued into the bulk. And of course, if in this toy model we allow this y to go off to infinity, the manifold will be non-compact. At the level of this toy explanation, I'm just stopping the radial evolution at some fixed value yc, but there are ways to get smooth solutions where this ends in a smooth way. For example, by using a generalization of then filling called Anderson filling, and I'll talk about that in a little bit. So let me call lambda c the size of the smallest circle, this T6 in the toroidal cross section. Okay, then the proper size goes as lambda c times the exponential factor from the metric. So we get this small proper size, but it has a simplifying property that is shrinking very slowly, right? Because the derivative of this proper size with respect to y is much smaller than 1. Okay, so in this case, it's easy to evaluate what the Casimir energy is, right? The Casimir energy is basically an energy density in 11 dimensions. Okay, so it will scale like 1 over RC to the 11, 1 over the proper size of this cycle to the 11. Okay. And again, the minus sign is important. It comes because we're using antiperiodic boundary conditions for fermions. In terms of the comoving length, then we'll get this power of e to the 11y. Okay. And then basically we have to solve the semi-classical equations of motion that are supplemented by this quantum contribution from the Casimir energy momentum tensor. So that's the idea. At this stage, let me make 3 remarks. So the first is we learn from this formula that the Casimir contribution is strongly localized near these cusp regions because of this e to the 11y. Okay, this means that Casimir energy is distributed in homogeneous way. So we'll have to include the back reaction of that on the metric, and I'll talk about that in a little bit. Now, this is a quantum effect, so we have to make sure that it's large enough so that it can compete with the classical sources. We'll see how that comes about, how that can be done. But at the same time, we have to make sure that other quantum corrections are suppressed. And one can show that this happens if the curvature size of the internal space is stabilized at a much larger value than RC, and both are much larger than L11. Okay, so in this case, we only get to include this leading quantum effect from the Casimir energy. So let me combine these three ingredients we described at the level of the homogeneous potential, and then we'll consider what happens when we include back reaction. Okay. So we basically, as I said before, we have to integrate the energy sources over the internal space, and we like to understand how they can, how they contribute and how they can give rise to an interesting minimum. Okay. So we have three types of contributions. The first goes like 1 over L square. That's the usual curvature contribution. I've written a coefficient A here that will play an important role for us. It basically accounts for the fact that the background curvature of the hyperbolic geometry gets corrections from warping and back reaction. So for now, I'll keep this number A, but I'll then argue that this A can be chosen to be small. Then we have the usual flux contribution. It goes like the number of brane square divided by volume square. Okay, so in terms of L hat, defined as the curvature radius in units of the Planck length. So the first term would be 1 over L square. The flux is 1 over L to the 14. Okay, because it's 7-dimensional volume square. Okay, and then the last contribution is the Casimir density we just understood. So remember, we said it goes like 1 over RC to the 11. Okay, but the internal space is rigid. That means we can trade out for a 1 over L to the 11. Okay. And then there will be a coefficient K that basically has the ratio between L and RC. Okay. So this is the basic structure we get. Okay. And we see that this quite minimal list of three ingredients has the right properties to yield a metastable solution with positive cosmological constant, because the negative energy source sits in the middle between the curvature term and the flux term. Okay. In particular, by balancing these terms, one finds a solution where L hat, so the size in units of the Planck length, is stabilized at order K divided by A to the 1/9. So if we can take K divided by A large, then we'll have parametric control, and we'll argue that indeed we can get A small. Okay, and moreover, this is a polynomial with three terms. So as expected, we can differently, like we can control differently the curvature of the potential and the height of the potential. Okay, and in particular in these solutions, we'll get near cancellations of the different terms, we'll get scale separation, okay, meaning that the internal size becomes much smaller than the de Sitter size. So this was at the homogeneous level. So the main message so far is that from these three ingredients, we get the right structure to get the de Sitter minimum. But now, of course, we have to understand what happens when we include back reaction that is driven precisely by this property of the Casimir energy that is strongly localized near these thin regions, like near these cusp regions. Okay, so to account for that, we have to consider the following metric ansatz. So besides our de Sitter for metric, we need to allow for a warp factor, e to the 2a. I'll often call e to the 2a-u. Okay, and also in the internal space, there will be modifications. The conformal mode will generally be activated. And also there will be metric deformations orthogonal to this volume mode, to the conformal mode. So this becomes a PD problem with 7 variables because we have a 7-dimensional space. Of course, it's very hard to solve, and I'll make some brief remarks about that towards the end. Here, instead, I'll focus on a more semi-analytic approach to understand this problem. So one useful way to organize the problem is to think about an off-shell effective potential that is completely equivalent to the 11-dimensional equation of motion and includes the effect of warping. So this was found by Mike Douglas a few years ago. So it looks very similar to the potential we were writing before, but notice that it includes the effect of this warp factor U here in the volume element and in the gradient term, okay? And Mike showed that in order to get the correct 11-dimensional equations of motion, one has to supplement this potential by Lagrange multiplier C, whose role is very intuitive. It's basically fixing that we're working at fixed G Newton. Okay, and if this C is chosen to be the 4D curvature scale, then one can prove that extremizing this potential with respect to U and the other matter fields is the same as the 11-dimensional equations of motion. Okay. Here, I want to know that the extremization of the potential with respect to U, which is the same as the time GR constraint, has a very simple and suggestive form. Here you find it. So notice that this is a Schrödinger problem where U is a wave function, okay? And the Schrödinger potential is basically minus the potential density from here. So there is a right-hand side that comes from this C. But as I said before, usually this C can be tuned to be much smaller than each of the individual contributions to the potential. So in many cases, it's enough to neglect it, although one can also take it into account, of course. But then it's important to realize that this has a form of a Schrödinger problem that provides a lot of intuition for different properties. Okay, and here I'm just showing again the fact that if one extremizes, if one solves the constraint, which is the Schrödinger problem, and also extremizes the effective potential with respect to the other fields, this reproduces the full 11-dimensional equations of motion. Okay. So let me just list some general properties that can be understood by using this effective potential. The first is we understand that we can get this important tuning A much smaller than 1, because we see that what contributes to the curvature is not just the background curvature, but there are also corrections from warping, like this gradient term. Okay, so by choosing discrete parameters in our compact manifold, it's possible to nearly cancel regions of negative curvature with regions of positive curvature. Okay, and that's the origin of this A much smaller than 1 tuning that we need. Okay, remember that tuning is needed so that the Casimir term, which is a quantum term, can compete with the classical sources. I'll also say that, well, Douglas proved that the naive conformal factor instability at large momentum is stabilized by warping. So that's an important property. Also, warping provides a bound on negative energy. Okay, and the way to understand that is that if we get a region, say, where Casimir is growing too much, okay, this negative Casimir energy is contributing positively to the Schrödinger potential, which means that the wave function will transition into a classically forbidden regime, and it will decay exponentially, and it will shut off that excess of negative energy. Okay, so that provides a bound on negative energy. And also we have derived that the warp factor provides a universal positive contribution to the mass matrix of all the metric fluctuations. Okay, so these are some general properties. Now I want to change to show you an explicit de Sitter solution, a smooth solution in one of these near cusp regions. Okay, that then will have to be glued onto some compact part. And again, I'm focusing on this near cusp region because that's where inhomogeneities are concentrated. As will become clear soon, it's enough in this case to just focus on the real direction, because the angular directions become important once we try to glue onto the bulk. Okay, so for now, I'll just consider a metric that depends only on this single radial direction. That's quite simplifying because we get ordinary differential equations instead of partial differential equations. Here's the metric ansatz. As before, it will have some warp factor. There is a radial direction, and then there are two say fields. One comes from the Casimir circle, RC. Here, just for simplicity, I took 5 of them to be equal. Okay, and in the last term, I'm incorporating this Anderson or then filling, which will basically be a cycle that shrinks smoothly and ends the space in a smooth way, instead of having to just end it by hand at the wall as we did before in the toy model. Okay. And here in the left-hand side, I'm showing one of these numerical solutions that leads to a DS4 in the space-time. Okay. So let's begin with the orange curve. Okay. So the orange curve is R. Okay. And you see that at y = 0, R goes to 0 linearly. That's precisely this Anderson or then filling that is ending the space there. In physical terms, we would say it's like the horizon of a black hole, except that it's a space in a space direction. Okay. And then the green curve has a warp factor, and the red curve has the evolution, the radial evolution of the Casimir circle. Okay. And the idea is that
there's a question. Edward has raised his hand.
Excuse me, I'll postpone.
Okay. Okay. So this is a local solution, and the idea is that at some point around here, we have to glue it onto the bulk. Okay. And on the right-hand side, I'm showing how the energy sources evolve point-wise. So this is the warped curvature. The flux, as expected, doesn't play an important role in this near cusp region. It's localized in the bulk. Okay. And the blue curve is the negative contribution from Casimir. Okay. And one can check that by integrating these energy sources, they all these two are competitive. Okay? And in particular, note this example already locally exhibits what I said before, that there are regions of negative curvature, like here, negative curvature contributes positively to the energy, and regions with positive curvature here and we can think about balancing them to accomplish this small a. Okay, so this was a local solution. Then the next step would be to glue this onto the bulk. A way to build a finite volume hyperbolic manifold is to start Hello?
Now we can hear you.
Can you hear me?
Yes,
Can
now we
you hear
can.
me now?
Yeah,
Okay.
and
Yeah,
you have 5 minutes left.
Good. Yeah, I'm almost done. So I was going to say, so we have to build now a finite volume compact manifold. We have to glue together these polygons. One difference with flat space is that polygons in a hyperbolic manifold also include hemispheres. Okay, and they are important in order to get finite volume because they stop this, growth towards, say, the boundary where we get infinite volume. Okay, and these hemispheres are precisely what source the dependence on the angular variables. Okay, so here we're focusing here on the cusp, but we'll be sourcing these angular directions. And at that point, of course, this becomes a PD problem with 7 variables, which is very hard to solve. The main point I want to make is that it's a completely explicit problem. Okay, and we have started exploring a promising direction, which is to use neural network methods to approximate these solutions. Okay, so the idea is that we construct a loss function that is the sum of the equation square, and we use neural network ansatz in order to minimize this loss function, okay, and provide an approximate solution. And we have started this in the first non-trivial example, which is H3, and there we have found examples of solutions that work to a good approximation. Okay, so I'll just end there. So in summary, we have found a simple mechanism to obtain DS in M theory that uplifts the Largan limit of M2 branes, and it uses negative curvature and the automatically generated Casimir energy. Okay. We have given arguments for the existence of the solution beyond the homogeneous level. We are currently thinking more about tackling directly this PDE problem. Okay. Now, as I said at the beginning, for us, it's very important to have an understanding of holography in these cosmological spacetimes. Here, I'll just say that such uplift realization of the DS-DS correspondence. And recently, there has been interesting and exciting progress in also understanding the dual of DS by using TT-bar type methods. So that's another interesting direction we are pursuing. Okay. And one last comment at this level is that the framework I was presenting can actually also be used to find more general cosmological solutions with accelerated expansion. And the idea is that one constructs a slow roll functional in the landscape and evaluates it to try to decrease it. Okay, thank you very much. I'll end there.
Let's all thank Gonzalo for a wonderful and well-timed talk. So there was a question by Edwards.
My question is just this: to make the Casimir effect compete with classical effects, did you start with an infinite family of hyperbolic manifolds such that the diameters of some cycles can be parametrically small?
What was important was this ratio that I gave here, this ratio K over A. That's what matters. So K indeed is related to the ratio between L and RC, but this A appears there. And what we used at the end is that this A can be tuned to be small by near cancellations of regions of positive curvature and regions of negative curvature. So indeed, we need some amount of small cycles to make this important, but it doesn't need to be super tiny, because what really care about is the ratio between K and A.
Well, there I can see 2 possibilities. One is that you just hope that there is a hyperbolic manifold where numerically things work. The other is you might have a family of hyperbolic manifolds that approaches some kind of singular limit, such that if you're far out on the family, parametrically, it will be guaranteed to work. I was trying to ask which of those 2 is the way you're looking at it.
Can you repeat the first option? I couldn't hear it.
The first option is just that you might be lucky and find a manifold where numerically some cycle is small enough so that some Casimir energy is big enough. That's one option. That would be a little bit more like what people usually have with flux compactifications, where you don't have things working parametrically. What would be better would be if you had, I don't know if it happens in 7 dimensions, in 3 dimensions, you can have an infinite family of smooth hyperbolic manifolds that approaches a singular configuration, such that parametrically you'd have small cycles if you're far enough out in the family. So in that kind of scenario, you'd be guaranteed possibly that it would work, rather than just hoping that numerically it manages to work. My question is, my question is,
I think there are examples like that in higher dimensions also, that mathematicians have studied that can.
Are you built into your story so that parametrically, when you claim something is big enough or small enough, is that supposed to be true parametrically in your work? Or are you simply hoping that numerically it's big enough or small enough?
Well, as I said, I mean, well, parametrically, I mean, here the parametrically large number is this K over A. That's what I'm saying.
Well, I've lost a little bit what it was, but I'm
just saying it's not just K. We care about the ratio K over A.
But the mathematical question that you asked, there are explicit examples like that. This Anderson paper gives those examples. So,
well, do they have the right property for your construction? Is your analysis based on examples with infinite families so that you can make parametrically valid statements?
The cusp can be parametrically small in the way that you suggest, and there are explicit examples with right-angled polygons that have been that you can find in our paper that were discovered recently that show that.
And your assertion is that then parametrically, whatever inequalities you need are satisfied?
Well, what we showed is that in those examples, the cusps are an order 1 part of the volume, that in the local solution, A starts out a little bit less than 1, and that the discrete parameters in this construction, including these ones involving the Anderson filling, allow you to tune A. There's a way to go up in A, there's a way to go down in A explicitly in the discrete parameters.
Okay, thank you.
Next one is Ivano, please.
Yes, hi. Thank you for the very nice talk. And the paper is also very nice, but I was wondering, I suppose my question is at least somewhat related to the previous one. More in general, what are the possible subtleties regarding, control and stability of all the constructions? Not necessarily just the hyperbolic manifold itself, but anything else that could go wrong, essentially.
Well, okay. I mean, as I said at the beginning, one thing that is very helpful here is this rigidity property.
Right. Yeah.
Right. That is quite helpful in order to stabilize most of the directions you could think about, like these, like these metric fluctuations that are orthogonal to the conformal mode. They all get masked because of this most of rigidity. What can go wrong? Well, I don't know. I mean, for example, you could worry that this negative, this Casimir energy produces a tadpole for RC, for example, right? Because it goes like 1 over RC to the 11 and is negative. So it will try to just shrink RC and produce a singularity like that. You could worry about that. But as I said very briefly here, that is actually avoided by the warp factor, right? Because once this RC starts to decrease and the Casimir becomes competitive with the other sources, it will change the sign of the Schrodinger potential, and it will send you into this classically forbidden regime where the warp factor will shut off that because it will decay exponentially. So, yeah.
So essentially,
I should also say, yeah, sorry, go ahead.
I'm sorry, I was just saying, what it seems to me that you're saying is that everything is controlled within a dimensionally reduced effective field theory, so there's no subtleties.
Well, as I said, I mean, here, for example, I showed an example of a local solution that was evolving in the internal space. That, of course, goes beyond just a naive, homogeneous approximation where you do dimensional reduction.
Yeah.
So far, I mean, we have various indications that the solutions are stable. We do not have a complete proof yet, but we're as we say in the paper, we're working on that also. Yeah.
Okay, thank you very much. Thanks.
I think we have time for one more quick question, Ben. No?
Sorry, is it my turn?
Yeah.
Thanks for beautiful talk. Most boring question. What is the SUSY breaking scale? So you have a couple of scales in your compactification here, right, from these small cycles. And it seems like that shortest length scale is probably the SUSY breaking scale. Is that correct?
Yeah. Here, SUSY is broken at the high scale when we compactify on the hyperbolic manifold. Yeah.
Right, but it's the shortest. I mean, you have these cycles that are degenerating, and then you want to get Casimir energy from them. So those boundary conditions break SUSY at that short scale, right?
I think we might have lost Gonzalo.
So maybe
Yeah.
we go to the next talk.
Yeah, maybe we can go to Jeff's talk.